So I think we can get started now. So is everyone able to see my screen?
Yes, sir.
Sure, thank you. Uh, yeah, so welcome all of you to this online problem solving session in the NPTEL course on modeling and simulation of dynamic systems. I am Parth Joshi. So I am a PhD student in the Department of Mechanical Engineering at IIT Bombay, and I am basically a Prime Minister's Research Fellow scholar, and as a part of this fellowship program, I got this opportunity to interact with you for this course. Thank you to NPTEL uh, for giving me this opportunity. So, this was a short introduction about myself. So, I'll be conducting these sessions every week for all of you. So, these sessions are basically problem solving sessions, which means that these sessions are like meant for uh, answering your doubts, questions, anything. So there is some content that is posted every week in the NPTEL online course, and so hopefully all of you have gone through that. So if you have any questions or any queries related to that, so you can ask those, or if you have any problems of your own that you are facing a difficulty with, so you can also ask those, and I will also be sharing with you some kind of sample problems which are similar to those kind of problems which you will see in the weekly assignments. So uh, this was about the purpose of this whole session. So yeah, so again, thank you all for joining. So can we have just a quick kind of an introduction, like uh, so all of you are from which background, so that it will help me in kind of deciding how to go about these sessions. Yes, Ritik Kumar, you have, I think, raised your hand.
Hello, sir. Hello, sir.
Yes,
I'm Ritik Kumar.
yes.
Currently, I'm pursuing in my BTech second year from the RGPB University, and uh, I'm also interested in learning the MATLAB and simulations. And
Okay.
I have the background of mechanical engineering. I have done diploma, so I
Okay.
have basic knowledge of CAD drawings. So I want to upgrade my skill to the MATLAB and simulation. That's why I'm doing this course with NPTEL.
Sure, sure, sure. Thank you. Thanks, Ritik Kumar. So anyone
Thank
else
you.
wants to share about their motivation and introduction? Yes, yes. Bishal.
Yes, sir. Uh, Sir, it's me, Vishal Sapkota. I am from Chennai. So currently, I am studying masters in power system.
Okay.
Uh, so why I choose my this NPTEL course, because my thesis related to the simulation of the dynamics.
Okay.
So it will be more easy for me for the execution of my research project. So for that purpose, I have joined this session, sir.
Sure, sure. Thank you. Thank you.
Thank you.
Yeah, thanks. Anyone else wanted to share about their like introduction? So some of you are from undergraduate program, some of you are from masters, so some of you are from mechanical, and some of you are from electrical background. So yeah, so I think it's a mixed audience. Anyone else wants to share their about their introduction and their motivation to join this course? not, I think then we can just get started with the current the content for today. So then, any one of you have any questions or comments related to the course content for this week? So if there are any questions, so you can stop me at any point of time and ask, like you can just unmute yourself and ask your question, whatever it is, or you can type it in the chat if you think. So, but I don't think I will be able to see the chat because I am sharing my screen. So I think it's better
Yes,
if
sir.
you, yeah,
Uh,
yes,
while learning this video, no, sir, that simulation of system using MATLAB,
yes,
there is one uh, analog diagram where it's like critically damped, under damped. This kind of programming is done there. So it's very difficult to understand that programming actually done in MATLAB.
okay, okay.
So
So
that is my
so
question.
this was whom this is
It's
Vishal, right?
maybe, yeah, yes, sir.
Sure, sure. Yeah, so I think I'll be talking about that in this session. So since you
Okay.
are from, I think, an electrical engineering background, I think you may not have probably understood that, right?
Yeah, yeah, sir.
Is
Yeah.
that correct? Yeah, okay. So basically, just like in short, what it is basically uh, that it is basically related to mechanical vibrations. So depending on the stiffness, damping, and mass properties of that system, so we can actually classify the system response into like those three categories, like uh, underdamped, overdamped, and critically damped. So that actually depends on the values of whatever mass, stiffness, and damping properties. So and then the response, the nature of the response will change as per that. So we will be covering that in this session also. So I think hopefully by the end of this session, I think you can have a better understanding of that. I'll try to improve your understanding on that. So does that help?
Okay, sir. Okay.
Sure. Sure. Anyone else? So yeah, so this uh, I have given a list of all the topics that are like will be covered in this course. So in this week, we are basically looking at the introduction to modeling and simulation, and in the subsequent weeks, most of these topics will be covered one by one. So in the next week, we have the uh, topics like bond graph modeling, and then uh, we will also be looking at the basic system models for like different kinds of systems like mechanical, electrical, hydraulic systems. And then we will also look at how to develop the models of combined systems where we have a combination of, let us say, mechanical and electrical kind of systems, or hydraulic and mechanical, etc. So those are called like electromechanical or hydromechanical or whatever. So there we will be also talking about those kind of models. Then we will also be looking at techniques to find the dynamic response, or basically the response of the system with respect to time. And then we will also be looking at how to get the system transfer function. So generally we get differential equations which express the behavior of the system. So then we can transform those differential equations into a different domain by using, let us say, tools like Laplace transform. So then it transforms the time domain differential equations into S domain or Laplace domain. So from that we basically can obtain the system transfer function. Then we will also be discussing about tools like block diagrams and signal flow graphs, which help us basically to represent the different entities and activities in the system. And these tools basically help us in visualize and understand and represent the system in a better way. Then the other topics which are covered are like state space formulation, where we have, let us say, some uh, higher order differential equations with multiple degrees of freedom involved. So then for that we have a in time domain we can express these differential equation as a state in a state space kind of form, where we transform, let us say, higher order differential equations into a system of uh, first order differential equations. Then the other topics like frequency response are also covered. And then,
Sir,
yes,
sorry for disturbance, sir. Current slide we cannot see, sir. We are seeing like overall slide, but current slide, yeah, yeah, now it's okay.
okay, sorry, yeah. So, no, are you able to see the slide on topics to be covered?
Yes, sir. Now
Second,
looking.
Yes, we can.
you are able to see the slide number two, topics to be covered, right?
Yes,
Yeah, I'm only on that slide itself.
Yes, sir. Now we can see.
Okay, fine. Then we'll also be, so as some of you mentioned, like we will be discussing about how to use these tools like MATLAB and Simulink for system simulations, and the other topics like uh, parameter estimation and system identification, and some uh, thing related to optimization will also be covered in the latter part of the course towards the end. So in this week, uh, will be basically just introducing these terms of modeling and simulation. So the first lecture was on basically introduction to modeling. It provided the definitions of some of these terms like modeling, what is modeling, and what is a model, and what do we mean by simulation. And then in the next lecture, there were some examples of different kinds of models that were discussed, which involved, like, let us say, uh, electrical and mechanical kind of systems. And then uh, the some of the terminologies related to modeling of dynamic systems were discussed. Different types of systems, like, let us say, discrete and continuous, uh, and uh, like, let us say, static model and dynamic model, or physical model versus mathematical model. All these kind of terminologies were introduced. And then we have a lecture on the introduction to simulation, which basically discusses some of the aspects of a simulation, where we basically we get the governing differential equations from our, like, our model is basically that set of some differential equations, governing equations, and then we try to solve them. So that process is mainly called as simulation. And then some initial part of MATLAB has been introduced. So how do we use this tool, MATLAB, for simulations? So I think most of you, I think, must have got access to this software MATLAB. So for this course, I think you will be provided access to MATLAB license, right? So am I correct?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
So how many of you are already familiar with MATLAB? So can you just raise your hand? Yeah, I think many of you are familiar with MATLAB already, so that's good. So yeah, thanks for
sir. One more doubt, sir.
yeah,
Sir, as the prerequisites are there are no prerequisites.
yes.
So, will we be taught about these systems, dynamic systems, and discrete systems, the differential equations also?
Yeah, so differential equations, maybe some, like, I think you may need to know a little bit of like what basic differential equations, like how to solve, like, let us say, first order or second order differential equations. I think we may not be teaching how to solve the differential equations. I think that is something that I think it is kind of assumed. But I think if we have any difficulty, we can also discuss like those in we can take up those difficulties in this session also. No problem with that. But yeah, so I think as a from the course point of view, those things are kind of assumed that you kind of know how to like derive the get the differential equation. So we will be discussing about the process, like we will be just giving you a general framework, an approach of to develop the model. So you need to derive the differential equation and then how to solve those. Uh, so but I think we may not actually get into the the really the mathematics, like how to solve this second order or first order differential equation or even higher order.
Okay.
Uh, but yeah, we can deal with those difficulties in these sessions. So does that answer your question?
Yes, sir. And about systems, about dynamic systems and discrete systems.
Yes, so we will be discussing like different examples on like different kinds of systems and how to develop their models. Yes, that
Mhm.
will definitely be covered because that itself is
Okay,
the
sir.
topic. Yeah,
That was my doubt actually.
yeah, sure.
Thank you, sir.
Yeah, sure. Anything else?
No, sir.
Okay. So yeah, so let's get started. So I have some sample problems with me, so we can try to solve them. We will discuss and try to get the answers for them. Uh, so anyone has any questions? Anyone else has any other questions? If not, then we can just get started. So we have this simple question, so which is related to the different kinds of systems. So when a system or activity it is uh, probabilistic, what is it called? So any answers?
Sorry, sir. Can you please repeat the question again?
So so I have the question on the slide. Uh, when a system or activity,
Sir, the question is not visible.
it's not
Yes, sir.
visible.
Slide is not visible. Yes, sir.
Okay, so let me just share it again. So is it visible now?
Yes,
Yes,
sir.
sir.
So when a system or activity is probabilistic, what is it called? Any answers?
Yeah,
So
I think it's called stochastic system.
yes, it is stochastic system, right? So uh, so any idea why is it called stochastic? So basically probabilistic
Uh,
means yeah, someone was saying something. Yes.
okay, I was saying that it's called stochastic because we cannot. I think it's because you cannot determine its behavior. It's not deterministic. You cannot tell its accurate behavior in the next step.
Yes, right. Sure, thanks for answering. Yeah, so it's correct. So you rightly said. So what was your name? Good name?
My name is Casey.
Casey. Oh yeah, hi. So you are right. So when our system variables are randomly varying in nature, so then there is a probability associated with the occurrence of that variable. So then that is why it's called as stochastic or probabilistic. So now this we'll just move to the next question. So this there is a figure over here. So this was there in the slides if you remember. So this talks about the process of in basically design of a dynamic system, and some of these balloons which have been shown like block diagrams, classical methods, and bond graph techniques also. So we need to fill in basically the correct sequence of how do we go from the system to the simulations, like basically from dynamic system to system simulation. So we need to basically identify what are the missing steps. So generally, where do we generally start from?
Again, it is not visible.
It's not visible.
Slide is not changed.
Okay.
Yes, now it is visible.
So can you see my screen now?
Yes, sir. Yes, sir.
Sure. Yeah. So we see this figure over here, uh, in this which uh, gives us this process. So we need to fill in the correct sequence of these different steps. Those are given here. So generally, when we deal with design of a dynamic system, where do we basically start from?
We will start from the physical system first.
Yes, right. Yes. So you basically we have a physical system with us. So and then so all of these techniques that are given over here, these balloons, block diagrams, classical methods, and bond graph techniques. So they will help you in arriving at something. So what would be that? So from the physical system using these techniques, what?
The physical system engineering model, maybe differential equation computer simulation.
Yes, correct. Yes, exactly. So so based on these techniques, we get an engineering model, and then so that engineering model is basically a set of differential equations, and those we will use the computer simulations to solve these differential equations. So that is the correct answer. So the next question is about uh, an architect. So he generally makes a scaled down model of a building before we actually make the building. So which shows all the rooms and the outer design and interior design. So what is this kind of a model called?
Static physical model.
Right. Yes. So it is static because once we build this scale like model, so when architect builds this model, so it will not actually change with time. So it is a static model. And since it is actually a physical tangible model, we can see it, feel it, so that it's a physical model. So that's why it's called a static physical model. So so we have a list of four things. So which one of these is not used in modeling? Any ideas? So relevance in this context, it talks about
It
we
may be,
see.
sir, analysis, sir.
Yes, analysis is correct. Yes. So modeling. So in modeling, we do not talk about analysis. We do analysis after we have a model. So that is the correct answer. So relevance means basically we are going to select some part of the the properties which are relevant to our requirement or study. So aggregation means like we will basically uh, decide on the what are the relevant entities and then combine them and study look at the interactions in between them. And block building which basically talks about the same thing like that we define consider like the different entities as different blocks, and we construct a network of these blocks and show the interactions between the different entities of the system. So in the next question, we have two different statements related to an aircraft. So the statement P says that for an aircraft, a static system analysis may be sufficient to determine the stress in the wings during steady flight. And the second statement is for an aircraft subjected to time varying stresses during flight through turbulent air, emergency maneuvers, or hard landing, then for that we need to do a dynamic analysis. So, so are these statements true or false? Yes.
Only Q is true, right?
Any other answers? So just think about it again. So just look at these statements carefully again.
Maybe both P and Q are true.
Yes. So both statements are actually true. Uh, so why is that? Because so when the aircraft is in a steady flight, let us say when it is cruising, so in that phase, generally the lift force which is acting, so the lift force because of the air passing over the aircraft, so that is in equilibrium with the weight of the aircraft, and the thrust for which is propelling the aircraft forward, that is in equilibrium with the drag force exerted by the air. So then that's why the plane is essentially in equilibrium, or it's actually called as a in a static state. So that's why we can do a static analysis. It can be sufficient to get the stresses in the wings. And for time varying stresses, like for in some of the other phases of flight, not only restricted to the phases which are like the the things which are mentioned like turbulence or emergency maneuvers or hard landing, even for the climb phase, takeoff phase, the uh, the system is essentially time varying. So the aircraft is accelerating, its speed is always changing, its direction is also changing. So in those cases also a dynamic analysis needs to be done. So both the statements P and Q are actually true. Okay. So let's move to the next question. So here we have this diagram which is shown. So we have this a dynamic system which is represented by this S, and state variables are represented by X, capital X. Input variables are represented by capital U, and output variables are represented by capital Y. So the question says that when capital U and capital Y are known already, the process of finding S and X is called what? Like basically.
Synthesis,
Okay, why do you think it is called synthesis?
because we have the input variables, and we are also knowing the output variables what we want. So what we are actually doing is the synchronizing the input with the output variables with the system.
Okay, okay, fine. Yeah, so it in a way it can also be called a synthesis also, and it can also be called something else depending on like the way we know the. So you said like you used the word, I think you have the desired output that is known. Uh, so in other cases, like if we have a certain set of input and output variable combination, so we have a, let us say, large set of data where we have a data available for a lot of input variables varying with time and the corresponding variation of the output variables with time, and so we have, let us say, a large data set, and from that we find out what is uh, the dynamic system model and the relevant state variables. So that is called also identification. So that process is also called system identification. So we basically kind of go in the reverse way. We actually derive the model based on the the input output combinations that we have. So we generally do this. So in some cases when the systems are very complicated, so there we actually can do some performs a lot of experiments on the system. Let us say if we look at some, let us say, process in some industry. If for example we have a, let us say, grinding or finishing machine in some, let us say, bearing factory or so, there are a lot of in parameters which need to be fine tuned, and so what we generally do is that we can carry out lot of experiments on changing the different combinations. Let us say we have, let us say, 4 or 5 settings in the machine, so those are actually the input variables. So let us say we provide like, or those are actually our different parameters. So we vary the machine parameters on different settings. uh, like let us say if we have, like we have the way we have a fan regulator, we have different settings on the machine for each parameter, and for each, let us say, parameter setting we do a lot of experiments, and then so we observe what is the effect of the change of that on the the output. Let us say if we measure the quality of that output, so we have some variable, like some parameter which measures. So let us say for a bearing we measure, let us say, surface roughness or so, something like that. So then we have a large data set of variation of these input and output combinations, and from that we actually try to extract and derive the model, what would be the model, and then use that model later on to predict what can be the behavior of the system for some input which was unknown, or so basically that is what we talk about when we call as identification. So the next question is like, so there are like list of things like, which of these do you think is the example of a discrete system?
Number of students attending the class. This is, I think.
Yes, right. So number of students is discrete, definitely. The other options like water flow in a dam, it's obviously a like a continuous system, because it always keeps on varying with time. The time scale in the universe and all the other things are actually continuous systems. So okay, fine. So these were some sample problems which are similar to the kind of assignment problems that you would see generally. Now we will talk about some of the other uh, concepts related to these systems and models. So in the slides there was something which was mentioned related to systems and environments. In thermodynamics we also talk about these similar concepts. There we generally call them as systems and surroundings, and there is a boundary. So when we are basically analyzing certain system, so we define a boundary by which we we can distinctly identify that this is the system that we are studying, and then the thing which is outside that boundary, that is called either surroundings, or you can call it as environment or whatever it is. And based on the interactions between the system and its surroundings, or system and environment. So we call those, we can, classify those systems based on like the what are the interactions. Uh, so it can be an called as an isolated system or closed or open system. So depending on the what is the interaction that is allowed. So let us say if the system can like exchange matter with the surroundings. So there can be, mass inflow or outflow. So mass can flow inside this system and or go outside the system, or energy can if it can enter with into the system, or it can flow out of the system. So then that is called an open. If only exchange of energy is allowed, but there is no exchange of matter allowed, so then that is called a closed system. And in if we do not allow any exchange of matter as well as energy with the surroundings, so that is called the isolated one. So we can see a simple common examples. Let us say if we have this kind of frying pan in the kitchen, so there is a exchange. So you can see water vapor coming out of the pan. So then there is matter being exchanged with the surroundings, and there is energy also which is flowing into the system as well as outside. So that is an open system. Now, if we just place a lid on top of that frying pan, so then there will be no exchange of matter, or negligible exchange of matter for that matter with the surroundings. But the cooking gas is supplying heat energy to that pan, so energy is able to enter or exit the system. So that is called a closed system. Now here we can see in this figure, which is a kind of a thermos flask. So then it's insulated. So then it will not allow anything to come out of it or enter into it. Or there is also, it's also insulated from, there is no exchange of heat that is occurring with the surroundings. So that's why it's called an isolated system. So we can apply the same analogy which we use generally in thermodynamics kind of context. So similarly, we can also apply it into this course on systems modeling. Any questions? Now let us apply some of these ideas to uh, so whatever we learned. So there was an example on hydroelectric power plant which was discussed in this one of these lectures. So here this system is actually huge in scale. Like, so there is a reservoir somewhere where we collect water and then hold that water, and we construct certain conduits by which we can allow this water to travel somewhere to a place where we have a turbine installed. So we allow the water, so the potential energy of that water in the reservoir, so that can be transformed into kinetic energy. So we generally uh, the turbine is placed at a lower elevation than the reservoir, so that conversion of the potential energy into kinetic energy is allowed, and then that water will enter into the turbine, and then the turbine will produce mechanical energy, and that will drive the generator which will produce electrical power, and that will be transmitted to the load. So this is the system overall. But if we are, let us say if we take an example where our goal is so when we are studying different parts of the system, let us say our goal is to analyze just the pressure distributions on the walls on the reservoir. So then what part of the system would we be looking at? So then now in my question, basically what I mean to say is that where will we place the boundary here? Any ideas on that?
It be only till the reservoir.
Right, exactly. Exactly. So since we are just interested in the pressure distributions on the walls of the reservoir, so we will just look at the uh, reservoir part only. So then we will get the hydrostatic pressure distribution. So the pressure variation of because of the depth. So because of the gravity, so the pressure will increase with the depth on. So that's why the reservoir wall is actually made thicker as we go deeper and deeper into the water, so as to withstand that pressure. Now if we want to analyze uh, the energy losses uh, as the fluid or water flows from the reservoir to the turbine, so then which part would we be interested in? Where do we place the boundary now?
From reservoir to turbine.
Correct, correct. So because the water inside the reservoir is essentially static, so then there is the pressure at a certain depth is the same, so there is no fluid flow actually happening within the reservoir, so the fluid will start flowing after the reservoir, and then till it reaches the turbine. So that part is the thing that we will be interested in. So now because of the friction as the water flows through the conduit and penstock, so there will be friction of the water with the walls of the pipe, and because of the viscosity of the fluid or water itself, some energy will be lost as the water flows. So then to study that, we will be restricting ourselves only to this boundary that is shown over here. So now if we are interested in determining the mechanical power developed by the turbine for some given fluid flow rate, so then where do we place the boundary now?
On the generator.
On the generator?
Maybe turbine to governor.
Sorry?
Turbine to governor.
Yeah, maybe. So it's basically around the turbine itself. So there is some part of the fluid which is entering the turbine and some part of the fluid that is actually leaving. So there is net mass flow in to the turbine and out of the turbine, and there is some mechanical power that is coming out of that turbine. So we can place the boundary somewhat like this. So the fluid flow will, because basically will do some work on the turbine blades, and that will produce some mechanical power out of that shaft, and that shaft power is basically driving that generator. The function of the governor is somewhat like different in the sense that any idea what is the function of a governor?
Governor means regulating the speed.
Yes, yes. So governor will basically try to maintain the speed also constant or nearly constant. So that is generally used in many diesel engines also. Uh,
To store the kinetic energy.
yes, exactly. So similar to a flywheel principle. So you see basically the idea that when we are depending on how what is our goal or requirement, we basically vary what is the part of the system. So the system is there in its own place, but we will only look at the parts which are relevant to us. And so So that's why like we have to place the boundary suitably in when we do any analysis, so that we only look at the parts which are relevant to us. Now similarly, if you want to study how much is the the electrical power developed by the generator for a given mechanical power developed by the turbine, so then now where will we place the boundary?
From turbine to governor.
Right. So it will be around the generator itself essentially. So the mechanical power produced by the turbine is basically driving the generator, and there is some electrical energy that is being generated out of that. So so then that so our boundary will be basically just around the generator itself. So you can see that in each stage of this system, so there is some kind of energy conversion happening. So from reservoirs, like the potential energy is being converted to kinetic energy, and then the kinetic energy of the water is being uh, converted into mechanical work in the turbine, and then that mechanical work is used to generate electrical energy in the generator. So basically in different in this system or any other kind of system, so there are basically energy conversions that are happening. So we convert one form of some energy into some other useful form which we want. So this is one example. So in a thermal power plant, we basically try to use the thermal energy. So we basically heat a water and like produce water vapors at very high temperatures, and then that energy is being used to spin a turbine. So essentially we'll again be using again some kind of a turbine, and then that turbine will spin and produce basically electrical energy, will drive a generator and which will produce electrical energy. So depending on the parts of the whatever system that we are interested in, we place the boundary suitably. Now instead, now we looked at the turbine and the generator separately. Now if you want to find out how the electrical power developed by the generator, how it depends on the fluid flow rate into the turbine. Now how do we decide the boundary now?
I think you put the boundary from the generator to the turbine, to the input pipe from to the turbine.
Right, right. So it will be basically placed around both of them. So we will be looking at the input of the turbine, and then the what is basically coming out of the generator. So the electrical power is coming out of the generator, so that so we can place the boundary likewise. Now if we want to find out what are the electrical power losses during transmission from this source to load, then our boundary will be what will be our boundary?
Generator to load center.
Yes, exactly. So it will be the output of the generator to the load center. So the generator will also have its own power losses because of its own mechanical efficiency. But let us say if we are given certain electrical power output of the generator, then from the transmission lines there will be some losses during transmission, basically because of the what are called as I square R losses or etc. And so as the current flows, there is some non-zero resistance of the wires that transmit the electric power. So then we'll be we'll be inevitably losing some amount of energy in that. So that's why we try to reduce the current and step up the voltage to very high level, so as to reduce that I square R to a minimum value. So now we looked at the different parts of the system. Now if we now say what is our goal, we say that we want to analyze the what is the variation in the electrical power that is available at the load center with uh, how does it vary with the reservoir water level, then what will be our boundary.
From reservoir to the load center.
Exactly. So then when if we formulate our goal like this, it basically means that we are looking at the entire system together, because that is the start point and the end point. So then we will here in if we our goal is like this, so then we place the boundary likewise. So if you so I think hopefully by now you understand that as we change our goals, we vary the boundary accordingly. So let us now move to a different kind of example. So we talked about this hydroelectric power plant. So similarly, if so here what we did is we just tried to simplify and narrow down our uh, the part of the system which we are looking at. Now similarly, if we want to look at a vehicle suspension system and its response, like basically if we want to analyze how the effectiveness of the vehicle suspension is, like for a passenger who is sitting inside the car, if we want to analyze the how the passenger comfort is and how effective is the suspension. So for that we can simplify uh, the model of the car. So the car has lot of things. It has a body, it has a chassis, it has an engine, transmission, and all sorts of things. uh, there are a lot of interactions happening inside the car, and then the car body is also flowing through air, so there is some air resistance and all those things are there. But if we just want to look at the effectiveness of the suspension, then what we can do in that case, any idea what do we do in that case? So when we say our goal is to basically analyze the effectiveness of a suspension, now how do we look at the car? Basically, let us say car is our system, and so then what are the surroundings in that, and what is the interaction happening between the car and its surroundings? Any idea?
I think that we create a simple model like the one which you're showing us on screen, whereby M represents the weight of the car and K represents the spring. And I think for the damped force, for the damper, which is C, I think that's the shock absorber. So we have simplified it to that, and then they can just be considered to be fixed on the ground. But we know that in a car it's fixed onto the wheels. But since you said we need to simplify, we can just ignore all those.
Right, exactly, exactly. So even before that, if we look at, like, when we say we are looking at the effectiveness of the suspension, what we mean is basically the interaction between the car uh, and the road, basically. So the tires of the car are in contact with the road, and the tires are connected to the car chassis through the suspension and the axles, basically. So then there are some mechanical connections between. the car body as such, and the wheels and the so then we try to simplify this model into just one lumped mass. So if we just consider the entire car to be just one single lumped mass, which is called as M. So we just draw a block of mass M, which represents the entire car weight. And now the suspension has some flexibility. So it has the shock absorber, the term that you used. So basically it has some stiffness and or basically some elasticity, and it also has some damping property. So it basically tends to uh, dissipate energy as it moves. So then we basically try to lump these parameters into, basically try to arrive at some value of stiffness, where we draw this as a single spring, and then we also try to lump together the damping effect that is involved, so into a single value of, let us say, some damper. So this basically gives us a single degree of freedom, spring mass and damper kind of a system. So this is like a very very simplified model of a car interaction with a road. Now then we have our with this with this simplification, we will get some if we try to analyze uh, this basically this typical model. So whatever that is shown over here in the figure A part, so that is our system. And let us say if we consider our uh, state variable as x, so the state variable in the sense like where what is the current state of this system, so that is defined by this parameter x or variable x. So then that x is basically the displacement of that mass. So it will give us some idea of how much is the car body moving in response to the road conditions. So if the vehicle is moving over a rough road, so then this actually the wall which is shown over here, it will not be fixed. So actually if we it's actually upside down. So the car body is the mass M and the wheels are actually on the this particular hatched thing. So I think we have a better figure over here. Yeah, so we can actually show it this way also. So that is also known as a quarter car model. So let us say if this is, we represent this road surface by the curve shown over here. So the wheel is forced to be always in contact with the road, and the suspension is being represented by the spring and damper over here, and the entire car body is lumped into one single mass. So what is our input variable is basically the road surface contour, so which is y of t, and the response of the system or basically output is basically the displacement of this mass, which is x of t. So that is our output variable, so to speak. So we basically try to use this model to get some idea of how much is the displacement of the mass given a certain road surface. Now what would be the the desirable characteristic of an active suspension? So what would be the, let us say, the how would we want the x versus y like kind of thing? So any idea about that? How do we say when whether a suspension is effective or not? Let us say based on this model, let us say if you want to say something about that. Any idea about that?
Sorry, sir, what was the question? Can you come again?
Sorry.
I said, can you repeat the question?
Okay. My question is like, let us say if we represent this car interaction with the road in this using this model, and we have the input variable as, let us say, y of t, and our output corresponding output variable is, let us say, x of t. Then how do we say, like, let us say, what would be the desirable characteristic of the output variable for a given input, which is y? uh, how do we say that when would be when the suspension would be effective? Like, what is the characteristic of x of t based on
Well,
the
based on the characteristic equation, we have to check the nature of the square root. That may be real or unequal root, like that. Some characteristics. We have to look the behavior of the square root. Then, by analyzing like over damp behavior or critically damp, under damp, like this, I think we can analyze.
Yeah, that is correct. But even
XT
before,
should be minimum.
sorry,
XT should be minimum.
exactly,
Or
exactly. So no matter what, let us say some given some damper value and some spring stiffness, essentially the best suspension would be that where x of t will be just 0, irrespective of what the road surface is. So it will just keep on cruising at its same level. So then that will give the maximum passenger comfort. So now, but in reality that does not happen. So there is some up and down movement of the car that happens as it goes over different bumps. So we basically want the x of t to be as minimum as possible. So we try to design the suspension based on that objective generally. So now, as someone I think said that uh, we have to look at the characteristic equation. So yes, that is our like next step. So we you know try to derive the differential equation. So we arrive at this uh, differential equation. So in the interest of time, I am not going into the details of how do we get this differential equation. So I think so I would suggest you to refer to this book on mechanical vibrations if someone is not familiar. So I think you will be able to understand what I'm saying better from this reference. So what we basically do is we essentially apply Newton's second law to this particular system, and then we try to derive basically the differential equation in terms of x. So we get a second order ordinary differential equation. And to solve this, so let us say if we are looking at free vibrations of this system, so to find out that, we assume a form of certain form of solution, which is, let us say, some exponential kind of function, and then we substitute this form of the solution in the differential equation, and this is what we call as the general characteristic equation. And depending on the combinations of values of the mass, stiffness, and damping, so the value of s will change basically. So the roots of this quadratic equation, so it will have two roots. So depending on this combination of the value of c, m, and k, we will get the different nature of roots. So let us say when this term under the square root, if it is positive, then this quadratic equation will have two distinct real roots. So if the term inside the square root is 0, then the quadratic equation will have two equal real roots. And if this term inside the square root, if it is negative, then the two roots will be complex numbers. So based on that, the response of the system will change. So that is mathematically that is the nature of the roots will change, and then mathematically the mathematical expressions of the response of the system will also change. But essentially or physically, what is happening is that the combinations of the different damping and stiffness values will alter the response of the system, and that will change the behavior of the system. So if we have the case where this damping factor, whatever we call it as zeta, so or basically the term inside the square root, if it is negative, so that is that this case, so where we have two complex roots. So then the how this is how the response looks in terms of the initial conditions. So x0 and x dot 0, so basically those are the initial displacement and initial velocity that is imparted to the system, and then this is the response of to the free vibrations basically. So this basically contains sinusoidal terms, or basically sine and cos functions, as well as exponential functions. So it will have a certain particular nature, so that is called as underdamped. Now if we have two equal real roots, so then that is generally called as critically damped system. So then we get the response of this form which is shown over here, and based on the initial conditions we can find out the values of these unknown constants C1 and C2, and this is how the response looks like. Similarly, if we uh, consider an overdamped system case where the expression which was inside the square root, if it is positive, so then we get two distinct real roots, and then we get a function of this or response of this form, so that is called as overdamped system. And if we try to plot these responses for a certain given set of initial conditions, so then we see that for the case which is labeled as overdamped and critically damped, there are no oscillations. So it just goes to a certain maximum value and then just exponentially decays off. And whereas in the underdamped case, there are certain kind of oscillations. So if there is if it is undamped or zeta value is zero, so there is no damping present, so then the amplitude of the oscillations will not change with time. Whereas in the underdamped case, so there is certain energy that is always lost due to damping in every cycle that it does of the oscillations. So and therefore the amplitude of the oscillations will go on decaying with or decreasing with time. So that is how we that's why we call it as underdamped. And uh, so I think someone had asked about they were not clear about this uh, these three cases. So is it clearer now?
Yes, sir.
Okay. Yeah, so if it is like if you need some more help, I think you can either uh, just go through this reference, or else you can, like, if you have any other questions, so you can email me also, uh, or you put your question in the discussion forum, if in addition to this, if you have any doubts. So now so this was basically meant to illustrate how do we use now MATLAB to solve, or basically try to get some idea of the what is the system behavior if we are looking at, let us say, this particular case of vehicle suspension, let us say, or some uh, system which has a differential equation of this form. So then how do we use MATLAB now to uh, solve these equations? So I'll be now moving on to MATLAB. So is everyone able to see my MATLAB screen?
Yes, sir.
Okay. Yeah. So now I have a code over here, which basically uh, I am basically implementing the same thing which was shown, we just discussed right now. So we have a certain spring mass damper single degree of freedom system, and we, let us say, we assume a certain set of values of mass, stiffness, and damping, and try to analyze what would be the system behavior. So there are three different, sets of regimes, or the kind of response that we can expect. So based on the value of this particular c square minus 4 km, which we just discussed, that this is uh, the value of the expression inside that square root. So we look at the value of that, whether it is positive, negative, or zero, and based on that we try to uh, put the appropriate expression for the what would be the, so we have already derived analytically what is the the response of the system. The expression, mathematical expression, is already there with us. We are just using MATLAB now to uh, calculate what is the response for a particular set of values of mass, spring, and damping, and trying to use MATLAB to plot, or basically visualize the response in a better way. So, so what I have used over here is like, so I have used this term called Wn, so which is basically omega n, which is the undamped natural frequency of this system. So we can calculate that based on the value of, which is square root of k by m. These are the initial conditions x0 and x dot 0, the initial displacement and initial velocity. And we consider a time interval over which we are, we want to analyze what is the response. So we choose, let us say, 10 seconds, and we take a time step of 0.01 seconds, let us say. Uh, so we take a small enough time step so that we get a detailed idea of what is happening at each. So because MATLAB is able to work with, let us say, discrete time step values over here. So then we get the idea of the response uh, value at different discrete time steps using this particular method, and we are finding out the value of this damping coefficient zeta, which is c upon 2 root km. So we are calculating this. So essentially in this particular code we are using MATLAB just as a like a calculator. So instead of so what we will do, when we, if we want to use just our usual calculator, so then for that we have to uh, you know take every time step time value and calculate the expression of the response at every time instant, and then like keep on repeating that until we reach the end time instant. So what we will do, if we generally use a conventional C programming type of approach, we would generally write a for loop kind of a program where we uh, would uh, consider this time array. We start from the initial time step and keep on incrementing the value of time by the time step value, and at each time step we evaluate this expression of the response. Now in MATLAB we can actually greatly simplify this by using the matrix type of computations. So here I have, as you can see, I have not written any for loop kind of thing over here. I have just directly uh, written down the the expressions as it is, and what it does is that when I enter, let us say, so here all these quantities except for t, those all of them are just scalars, but the time t is a vector or a matrix for that matter. It's a just a one dimensional matrix, so that's why we call it as vector. So this, so when we calculate this part so of the expression, so because t is a vector, this value of this expression will also be a vector quantity. Similarly, we can also calculate this part of the expression, which is basically the sinusoidal response part. So it will be again, like, because it is calculated based on the time vector, it will again now be a vector quantity. So we basically have a set of the vector values corresponding to each time instant contained in these parts over here, so which is this highlighted part and this. So now we are using dot star operator over here, which is basically element wise matrix multiplication. So what it does for us is that we have this value of exponential function with respect to time for the entire range of time values, and we have the corresponding value of this sinusoidal part of the response uh, with respect to time. Now we use this element wise multiplication operator so that we can just get the for, so basically, let us say, uh, so if I try to represent this in terms of, like, if we look at, like, let us say, an Excel kind of analogy of this. So for every row in, let us say, Excel, uh, we could designate like every time instant and the corresponding row related to that for that time step. So we have a, let us say, column, first column representing this, and like another column which representing this. So if we multiply the corresponding values inside each cell of those two columns, this is what is basically happening over here. So by writing this line in this way, we just get the entire uh, the response value across the entire range of time values in just a single line. So what this has reduced is our effort in writing the for loop kind of a code. So we can still write a for loop type of a code, but this is not needed in MATLAB because it is already good at doing these kind of matrix calculations. Does that make sense? Everyone is able to follow what I'm saying?
Yes, sir. Yes,
Okay.
sir.
So I think some of you were already familiar with MATLAB. So I think you would, I think, be already familiar with this. But someone I think who is not familiar, I think for them, I think this is something which might be new, if at all they are not familiar. So this is like a peculiar characteristic of MATLAB by which we can make our code very compact when we write those, and we essentially try to write, we just write the expressions like the way we would write the expressions in our, let us say, hand calculations in our notebook. uh, that's the the good feature about MATLAB, that it greatly simplifies mathematical calculations. Yeah, so moving on to this, so we basically write an if else kind of uh, here like, so depending on what is the value of the expression inside this the square root, so that will decide in which zone we are operating in, whether we are in under damped or over damped or critically damped. And then we have the corresponding expressions for the response and the relevant, the terms. So uh, which are in those expressions. So S1, S2 are the exponents of the two parts of the solution, and C1 and C2 are the multiplying, like basically the constants C1 and C2. So this is how we write the response in case of the overdamped case, and similarly for critically damped case. So in every case we are using this dot star kind of operator extensively. And finally, by using this if else construct, what we end up with is essentially a vector x which contains the response of the system at every instant of time t, and depending on the combination of values of m, c, and k, our response will change accordingly. So right now I have set the values to these some arbitrary values, let us say mass, c, and k. So if we just look at the values of mass and k, the value of critical damping is 2 into basically square root of k into m, which actually works out to be 20. So it's basically 2 into square root of uh, k into m, which is 100, and square root of that is 10. So 2 into 10 is 20. So that is how we get the value of the critically damped, uh, uh, like that factor. So if our damping value is less than 20, it will be underdamped, and if we exceed beyond 20, it will be overdamped, and 20 will be critically damped. So now since our C value is 2, it's underdamped. So we would be expecting the response to be somewhat like this, which is the dashed line which is shown over here, which is basically a oscillations but with decaying amplitude with time. So let us try to run this code now. So we got the response with respect to time as expected. So we can see that this amplitude is decaying with respect to time, and the oscillations are essentially dying out until approximately 8 or 9 seconds, and by the time we come to 10 seconds it's almost zero amplitude. So this is the underdamped case. Now if we set the damping value to, let us say, 25, and now try to run the code again. So it now changed the response to this way. So what if we want to take a closer look at how the response looks like? We will zoom along the time axis. So what happens is that because it is an overdamped system, it will just with the initial conditions, it will just try to go to a maximum value, and then gradually it will fall off or decay with time without any oscillations. So that is called as overdamped kind of a response. And now if we set the value to 20 and try to run again, the response is actually similar, but if we closely observe, so if we just compare with our previous uh, whatever we just ran previously, so we can see that this so the figure 3 is for the critically damped case. So if we look at the first 2 seconds, or sorry, so if we look at the zoom into the first 2 seconds or so for both the figures. So I am basically using the MATLAB version 2020 so in that we have these user interface tools to manipulate the figure whatever plots which we have. So this was the critically damped case. So here it just the response just drops down to zero without going to any maximum value. So whereas in overdamped it goes to a maximum value and then falls off. So critically damped case actually settles down to its equilibrium position in the fastest time. So that is why critically damped is generally considered to be the the fastest response without any oscillations. So if generally we see that there are some kind of doors which have which can they have a mechanism by which they all automatically close. So those have some dampers installed in them. So basically those are piston cylinders filled with some kind of an oil, and generally they have an orifice which contains holes through which the oil is passed through that orifice, and that causes some uh, energy dissipation. So that creates a damping kind of effect. So it's essentially an piston cylinder kind of an arrangement in that. So those are generally designed to be either over damped or critically damped. So when we generally try to pull such doors which automatically close, so uh, so once we open the entire door and let it go, it slowly uh, closes uh, on its own. So that's the like the essential characteristics like of an over damped or like that kind of or critically damped kind of case. So makes sense. So is
Yes, sir.
everyone able to follow what I'm saying?
Yes,
Yes,
sir.
Yeah. So this is how we can use MATLAB. Now here we used it as a calculator. Now if we want to simulate uh, this system, so this is not exactly a simulation. We are because we already know the analytical solutions over here. We are using just the analytical expressions to calculate the response with respect to a certain time in a certain time interval. So we can change the value of the time. We can also change the value of the time step. Now, if we change the time step, the accuracy or level of detail that we get will reduce. So we will, when we actually reduce the time step, we will lose some information because we will be looking at the response at uh, time steps which are larger, then the accuracy of our analysis will reduce. So, but depending on the our requirements of the accuracy of our analysis, we generally decide a reasonable value of the time step required. So, if we just go on decreasing the time step values, the computational complexity will increase. So, it will increase the time required to solve and all that because we need to do the calculation. So, at every time step, so we need to arrive at a reasonable value of a time step based on certain engineering judgment that this is good enough. So that depends generally on the problem that we are trying to solve. But if we let us say if I just put the time step as let us say one second, so then we know that this is not going to be enough. So then we see that the figure that we get is grossly not correct. So we don't now since we have a time step of only 1 second, we don't know what is happening between 0 to 1 second. So then that's why this is not suitable for this problem. So so these are some small aspects related to simulations. So if we want to clear the command window, we use the command CLC. So that will just clear the command window. And if we want to close all the figures, we say close all. So that will close all the figure windows. So I have no figure windows open now. And if you want to clear the workspace, we can just either type clear or say clear all. So both are like largely equivalent. So now if we have some like a system where we know the response is like a underdamped kind of a response, so then there is a technique called logarithmic decrement, where this is like a graphical technique or analytical technique by which we can estimate what is the damping present on the system. So if we do a certain experiment and we get the plot of the displacement which time with respect to time. So what this technique does is that it compares the amplitudes separated by a certain, after successive cycles. So let us say if we are looking at a point somewhere here, so then this is mainly for the underdamped case. So it's like let us suppose if we are looking at this point over here in this particular, then we will look at the next point, the next amplitude, which is after one completing one full time period. So then this has come back to its maximum position. So in after completing one cycle or one time period, what is the extent by which this amplitude has decayed. So we try to estimate use that amplitude values. So either if we look at the corresponding value amplitude values from the graph or from the data that we record, and using these expressions we can estimate the what is the damping present on the system, provided that this damping is like viscous damping. Makes sense? Any questions till now?
No, sir, no.
Okay, so we just now looked at the uh, for a simple spring mass damper system, what is the the kind of response for to free vibrations. Now if we have a the car vehicle suspension type of model, so then we can apply that same model, so the spring mass damper system model, and we can basically apply this particular boundary condition over here. So whatever was the fixed end in this model, so this part was fixed. So now when we are looking at the vehicle suspension, so this is basically the thing which is upside down, as I mentioned, like, so this is the wheel and this is the car body. So the wheel is moving up and down as it travels over the road. So this is basically like a displacement boundary condition, or in some sense it is basically forced vibration. So it's forcing the system to move in a certain way by having the constraint that the wheel is always in contact with the road. So then that is forcing the displacement of the wheel to be in a certain way depending on the road profile, and based on that, so we get the response to forced vibration. So the x of t that we will get, which will be that will be the outcome of forced vibrations. So So when we calculate the response to forced vibrations, the solution that we get will have two parts. So it will be, what will be those two parts? Any idea? Generally, those two parts of the solution will be? So generally, when we solve, a non-homogeneous differential equation. So if this was a homogeneous differential equation, so the solution to this homogeneous differential equation is called a complementary function. And when this right hand side of this differential equation is non-zero, so then that is called as a non-homogeneous differential equation. So that response to the non-zero right hand side is called the particular integral or particular solution. So the overall solution will be basically a combination of this complementary function and particular integral. So here in this case, uh, so in case of forced vibrations, so there will be the response to the initial conditions. So if there are some initial conditions, let us say if there is some initial displacement or initial velocity of this mass x of t, if there is some initial velocity upward or downward or whatever, or if there is some initial displacement, so then that will cause some free vibrations. And then because this wheel is in contact with this road, there is some certain forced vibration, so it's forcing the uh, wheel to move in a certain way, which is in turn causing this mass also to, it is forcing it to move it in a certain way. So then that will uh, be the kind of a particular solution in that sense. So the combined solution to this entire problem will be the response to the free vibrations plus forced vibrations. So a superimposition of that will be the total solution. Now to like for example, if we consider a very bumpy road which has lot of bumps in every, so let us say if we can represent this bumpy road by a sine wave kind of a function, so then that is called as an harmonic excitation or sinusoidal excitation. So we are forcing this y of t to be in a certain way, and then we measure what is the response x of t to such kind of a excitation. This is also known as base excitation in vibrations, but the terminology is not important. So essentially what we are looking at is that if we force the system to move in a certain way, then its response is governed by its own damping and stiffness properties, and the motion that is being imparted, or basically the energy that is being injected into this system in every cycle of motion. So what we would expect, that there will be initially some transient. So like let us say if the car enters into this bumpy road, it will try to oscillate up and down based on its own behavior. Let us say whether it is under damped or critically damped, and then after a while, if this road pattern just continues for a very long patch, essentially it will the the motion of the mass m will essentially replicate the pattern that of the road itself. So now to solve this kind of a problem, we can similarly use MATLAB over here. So I have an example to demonstrate for you, for all of you.
Sir,
Uh,
one question, sir.
yeah,
Sir, for doing like this kind of problem, we cannot do by simulation by using the transfer function, sir.
we can use simulations,
Yeah.
but for for today's session, I do not have a because we are not yet into that uh, we have not covered that part in the course yet, so that's why I'm not put up that yet. But
I
yes,
thought,
we
yeah,
can do.
I thought it will be slightly easy, sir, when we go for like using the transfer function and
Yes.
looking the curve. So it will be like too much difficult for writing the code and just checking, writing all these equations. So it will be more complex and difficult to understand.
Yeah, it may be. uh, we will actually come to that eventually. uh,
Okay, sir. Okay.
yeah, we will also be discussing about using the tools like Simulink, and by which we use just like the transfer function kind of an approach to solve. But for now, we are just discussing about how we can use MATLAB here, like as a simulation tool for calculation and visualization kind of a thing. This is just a demonstration right now. Not We are not really going into the deep physics of the problem for now. It's just meant to be a demo for you to understand how we can use the different features of MATLAB. So that's why I have chosen this example, because I think everyone can relate to it. Does that make sense?
Yes, sir. Okay.
Makes sense, sir.
Sure. Thank you. Now, if we now this is generally called as the quarter car model now, because since a car has four wheels, so now we generally try to represent this the we lumped all the four wheels together, and we consider the interaction of all the four wheels together into a single lumped parameter. So we lump the entire mass together, and we lump the entire stiffness and damping of the entire suspension of all the four wheels together. So that is why it is just one fourth of the entire thing. So that's why we call it as a quarter car model. So now if we want to extend this model further, I have another like example demo for this. So then we what like here, if we consider that this tire is like essentially rigid. So here what we are doing is that the center of mass of the wheel, that motion is called as y of t, and we do not we are inherently assuming that the wheel is rigid. It is just following the center of mass of the wheel is just essentially following the mirroring the trajectory of that road profile. uh, so but if we want to go even further one level beyond that, we model the car body here by the mass m1. So this is the mass which is above the suspension, so which includes, let us say, the entire chassis, car body, and whatever is consisting like inside that. And m2 represents the four wheels together, and the k1 and c1, it's basically the stiffness and damping of the suspension part. Like the suspension springs will have some the stiffness and damping. And here we are modeling this tires as a non rigid body, so then it will again have its own stiffness. So the tire material, it's made of some rubber and it is filled with air, so it is definitely an elastic body, it is not rigid. So then it will have its own stiffness and damping properties depending on the material of the tire, and also like the air, it depends on the air pressure in the tire. So we can also model the tire stiffness and damping characteristics. And then we have this E of t, which is same as that the y of t that was shown in the earlier diagram. So E of t will be prescribed, or basically that is the road profile with respect to time. So that will be our excitation. to this system. So here, if we want to model it in this way, where we consider also account for the tire stiffness in addition to the stiffness of the suspension, then our model can be represented in this way. So it will now become a 2 degree of freedom system instead of a single degree of freedom system. So I took some sample values of masses which are representative of what will be for a some kind of a car. So we have some sample stiffness values which I have just arbitrarily chosen, and some damping values which I think are reasonable, uh, and we simulate this system, and then we can use MATLAB here now to find out what will be the response. So I have a MATLAB code for that. So here in this MATLAB code, we can actually perform like similar to a single degree of freedom system. We do the forced vibration analysis for this 2 degree of freedom system in this code. Uh, so we provide some initial conditions and the system data, which is the mass and stiffness and damping parameters. And for a certain set of initial conditions, which is basically initial displacement and initial velocity of those two masses, of like which represent the car body and the wheels. So let us say we here assume that there is some initial displacement given to the wheels, and the excitation is now modeled as a certain sinusoidal function. So basically the road profile is assumed to be a certain sine or cosine kind of a function, and we using that, we again, like as I just like I had discussed, that we uh, split the solution into two parts, which is basically the complementary function and the particular integral, or basically solution to the homogeneous differential equation and the non-homogeneous one. So the response to forced vibrations will be combination of both the complementary function and the particular integral. So we extract the damping and uh, mass stiffness and damping parameters. So I will not really discuss about the algebra part of that. So let us consider that it's an similarly we will use the analogous approach like a single degree of freedom system. We will basically, based on the nature of the mass, damping and stiffness, so it will govern the characteristic equation, and then roots of that characteristic equation will govern the behavior and decide whether the response is underdamped or overdamped or like that. And then we derive the particular solution based on the nature of the excitation, which is basically sinusoidal function itself. So it will be a sine wave with the same frequency as that of the uh, whatever the road profile variation. So as I said, like the response of the car will essentially try to mirror the uh, like once it settles down into the vibrations, it will essentially try to mirror the same nature of vibration of the excitation. And here we find out the unknown constants like the way we usually do by applying the initial conditions and combine the parts of the like the complementary function and particular integral, and we basically get the displacement, velocity and acceleration plots with respect to time in this code. And in this code I have also uh, provided a section. So right now I have commented it out, but we can also animate the motion of this particular system, so using this MATLAB code. So I'll just run this code for you right now. So the output of this code is basically the displacement of both the masses, so m1 and m2. So in our slide, which shows that the car body is being represented by m1 and the wheel displacement is represented by the m2. So what we can see from this figure is that the blue line has much lesser amplitude than the orange line, so which means that the car body does not oscillate with that much amplitude as compared to the wheels, so which shows that the suspension is somewhat like quite effective in containing that displacement of the car body to a minimum value. So that's how we, like, by tuning the values of this stiffness and damping, we can design this the response to be of a certain nature. So we can use these kind of tools like MATLAB for visualization of the response of the system to different sets of initial conditions and like damping, stiffness and mass properties. So we can manipulate the values of these parameters in the code and try to run for different sets of parameters and find out how the behavior changes for different sets of values. So I'll also show
Sir,
you.
this
Yes.
sir, this graph is just a plotting or a animated.
No, this is just a plot.
So, how can we get the results in animated?
So animated, for that, like, we have different like advanced functions for that. So what we do is, in an animation, is that we generate every frame of that plot in that plot. So I'm not, by animation I do not mean that the plotting is being animated. What I mean by animation is that I have tried to, when I show this figure to you, uh, so if I try to animate the motion of these blocks m1 and m2, so at the back end, the calculation of the, like, let us say, what is the displacement of this mass m1 and m2 is happening in the back end. And what we are showing in the figure is like how much is this mass m1 and m2 moving. So we can visualize that in a good way by using that animation. So that's what I meant by animation. So I think by seeing this video you might understand. So did I answer your question?
Sir, actually, I want to see the code in your MATLAB command window for this animated one.
Yeah, just I'll
Just a scroll, sir. Just a scroll.
yes, yes, I'll just scroll, but just you can see this video first. So you can see that
Yes, sir.
this dark black line is moving up and down. So that is the the wheel going up and down. But you can see that this block is hardly moving, but although this block is actually moving, so this is actually not moving much. So this is what is being shown over here, by which you can visualize this.
Yes, sir. Yes, sir. Got the point.
So there are like many features in MATLAB where so what I'm essentially using this is this video function, video writer. And in that we generate the plot, or basically so we run a for loop over the entire time interval, and we plot how this where this block, the coordinates, xy coordinates of this block at every time instant.
Okay, okay, sir.
and then we get we basically store every frame. So like at every time instant we know where that block is, like with respect to, let us say, if we in a 2D plane we want to or let us say if we want to, if I am throwing a ball and recording a video of it, so what at every point, and so video consists of different frames basically, or different sets of images. So in every video we capture where that ball is located in that picture or image. So similarly here we like when we are doing animation, we are recording the where that body has reached at every point of time, and store that frame, and then when we play that in a sufficiently fast way, then we see smooth motion or smooth animation like that. So that's what I meant by animation as such. So you can explore these different features of
Thank you,
MATLAB.
sir.
So it's basically just for visualization purpose. Physically, it's not nothing like we are doing anything like physically. It's just basically a feature which we can use for better visualization and better presentation as such. So you may explore these different features. Although this may not be part of the course as such, I am just showing you so that it may be helpful for all of you. Uh, Makes sense?
Yes, sir. Thanks for that scrolling. I just want to see that code because sometimes it gets error when I run the program
Okay,
in between.
sure. So that's all that I had from my side. So anyone else had any question or query related to anything that we covered today? Any feedback, any comments that you would like to share?
Yes, I would like to thank you for the interactive lesson. I think I've
Sorry?
learned, I said I'd like to thank you for the lesson. I think I've learned quite a lot.
Okay, sure. Thank you.
So session was really interactive, and the way you have explained and listened our questions very patiently, with your patience, we are really thankful for this.
Sure, thank you. Thanks, Ritik. So thank you very much all for joining. So let's meet in the next week on next Monday in this same time 7 to 9. So till then, in the meanwhile, if any one of you have any questions, you can always post on the discussion forum of this course.
On the same link, we can join on next Monday.
Yes, the link will remain the same. Yes.
Okay, sir.
Thank you.
Okay, sir. Thank you very much.
Thank you.
Thank you, sir.
Yeah,
Thank you, sir.
thanks. Thanks. Thank you all for joining.